Hello everyone. Today let's look at this problem on Michael's bratwurst sausage. First of all, you may want to take a pause on the video just to read the problem. Now let me give you an example on how to calculate Michael's profit. Okay, suppose that Michael orders 140 sausages at $1.50 each. And also, let's say the weather turns out to be good, which means the demand is 120. And let's say he also requests the food processor, so that means the food processor will pay him a $0.50 for the 20 unsold sausages he has. In this case, his profit can be calculated in this way. All right, here's a long expression, so let me go through this expression with you. So profit is simply revenue minus cost. So let's find out the revenue and costs. First of all, the sales revenue is here. So each sausage is sold for $5 in retailing price. And here, you order 140, but the demand is only 120. So that means you can only sell 120 sausages. Okay, I use mean here just to represent that the actual sales of the sausage is the smaller of whatever you order and the actual demand. So that's the sales revenue. Minus, well, here's the ordering cost. Each sausage costs him $1.50. He orders 140 sausages. Whether he sells all of them or not, he needs to pay for all of the 140 sausages. Since he requests the food processor, the food processor will buy his unsold sausages, which is the difference between what he orders and the demand, and each sausage is paid 50 cents. Okay, so this is the revenue from food processor. And by the way, it also mentions that if he requests the food processor, he needs to pay a $5 handling fee. So this is a handling fee. Okay, so if you carry out the calculation, it comes out $3.95 as his profit. And the question is quite simple. So in this situation, how many sausages should Michael order every day to maximize his expected profit? What will be his expected daily profit in that case under the best decision? And you need to build a decision tree to analyze this problem. Now let's build a decision tree to analyze this problem. This analysis has 3 steps. First, you build a tree to capture the problem. Second, you provide the payoffs of each possible outcome. Third, you fold back the tree. Okay, so these are the 3 steps that we're going to follow. In the first step, building a tree, we are going to build a tree from left to right, following the so-called sequence of events. The events that we're going to identify are either decisions or uncertainties. Decisions are the events where we decide on something. Uncertainties are events where we cannot control the outcome. Okay, so decisions are the ones you control the outcome. Uncertainties are the ones that you do not control the outcome. And you build a tree following the so-called sequence of events, which essentially means you simply ask yourself, so what's the next event? So let's start building the decision tree. The first event is Michael needs to decide how many sausages to order. This is a decision because he chooses. So I'm going to draw a square to represent decisions. Just to remind you, square represent decision, circle represent uncertainties. You do not mix them up. If you use the wrong icon, you use square instead of circle when it's actually should be square, you'll be taking points off. Okay, so anyway, so there are 2 options. One is order 80, one is order 140. So I create 2 branches. Also, when Michael places an order, he incurs a cost. Okay, the ordering cost. And my advice to you is whenever a cost or revenue is generated, you record it close to the branch. For example, when he orders 80, that's a cost of $2 per sausage. So that means he incurs a cost of 2 times 80, that's minus 160. Minus 160 means it's a cost, so that's why it's minus. Likewise, if he orders 140, that means he's incurring a cost of $1.50 for each sausage, and he orders 140. Now next, I'm going to follow each branch and ask myself, what's the next event? Let's start from this branch. After he orders 80, what's next? Well, the next thing is he will find out the demand in the next day. And the problem says that the demand can be either high or low depending on the weather. And weather is something you cannot control, so we're going to use a circle to represent that uncertainty. We know if the weather is good, the demand will be high at 120. If the weather is bad, demand will be low at 60. So that's why I create two branches. And also, I know the chance of having a good weather is 0.4. Bad weather is 0.6. So whenever I have a circle, just to remember to put the probabilities next to each branch to remind yourself that that's a probability for the occurrence. And when the demand realizes, that's also the time when sales is generated. So we can find out the sales revenue. If demand is 120 and he orders 80, that means he can only sell 80. Okay, so although demand is higher, but you are limited by the supply. And every sausage is retail for $5, so that means the revenue is 5 times 80. Likewise, if the demand is 60, he can only sell 60. Okay, 60 is smaller than 80. Demand is less than what you have, so you can only sell 60, which means the sales revenue is $5 each times 60. Okay, we got two more branches. Let's pick one to start with. I always goes with the one on the top. So this is a case where you find out the weather is good, demand is 120. What's next? Well, it says that when the weather is good, Michael can request a food processor to buy back any unsold sausages. He can request. So that means he can choose to request or not to request, which means that's a decision. So the next event is a decision, so I'm going to give you a square. Square represent decisions. Here the decision is to choose between requesting or not to request. So that means there are two possible outcomes. Two choices, okay? Request the food processor or do not request for the food processor. And by the way, if he requests a food processor, there's a $5 handling fee. And then the food processor will buy the unsold sausages. But look at this case. This is a case where the demand is 120, but he only ordered 80. So that means he will sell out all the sausages. So even if the processor comes, there's nothing the processor can buy. So that means Michael will simply generate the cost of the handling cost of $5. And what happens next? Well, it turns out no, there's no further event, so this is the end of the branch. If Michael does not request a food processor, and then that's it. There's no other additional cost or revenue, and there's no further event, so that's it. Move on to the next branch. This one, well, if the demand is low, there's no option of making the request for the food processor, so that's it. That's end. There's no further events. So now let's move on to this branch. Okay, so this is where he decided to order 140. What's next? Well, again, it's just similar to what he orders when he orders 80. The next event is, you figure out the demand in the next day. So again, it's an uncertainty with two possible outcomes. Demand could be high or low. Again, with the same probabilities. If the demand is high, okay, he ordered 140, demand is less than 140, so that means the revenue is $5 each times the demand. If the demand is low, okay, then he orders more than the demand, so his sales quantity is 60. So this is the revenue. If the demand is high, in this case, again, he can decide to request a food processor or not. So that's a decision, a square with two options. If he requests the food processor, okay, so this is a more complicated case. First, he generates a $5 of handling fee, and he orders 140. Demand is smaller than what he orders, so that means there are 20 unsold sausages that the processor will buy back. So that means in terms of revenue or cost, Michael generated $5 of cost, but he also received this amount from the food processor. If there's no food processor, then nothing happens. That's it. And if the demand is low, then there's no option of calling the food processor, and that's it. So this is the first step. We have a completed tree to represent the decision structure of the problem. Now, second step. We need to provide the payoffs for each possible outcomes. So again, payoffs are simply something you try to either maximize or minimize. Okay, so that's something you base your decisions on. In this problem, Michael wants to maximize his profit. So the payoff here is simply the profit in each case. Let's look at this one, the first one. In this case, he ordered 80, demand turns out high, and he called the processor, food processor. And now it's convenient because we record all the related cost or revenue along the path. So all we need to do is to add up those numbers. Okay, so this is why you want to write those numbers along the path, because now it becomes convenient. So first, he generated a cost of this, then he received a revenue of that, and then another cost of this for food processor. So just add it up. This plus this plus this comes out 235. So in this case, his profit is 235. Next case, similarly, just add up all the numbers along the path, which means this number plus this number, and that comes out 240. Next one, this number plus this number, okay, so that's 140. Next one, he incurs this cost, receive this revenue, and then food processor generate this cost or revenue. Just add all of them up, comes out 395. Next one, again, this number plus this number comes out 390. Finally, in this case, he incurs the ordering cost, generate this much of revenue, that's it, add them up, comes out 90. So this is the second step, providing the payoffs for each possible outcome. Now we can move on to step 3, folding back the tree. You build the tree from left to right, you fold it back from right to left. Okay, you fold it back from right to left to find the optimal decisions. So you always start your analysis from the note on the right, the notes that do not have following notes to their right. So that means we can start from here or here, doesn't matter. Let's say I start from here. It's a square. Square means you choose. So you compare the options and find out which one is better. Here, you can choose to call the food processor, which means you will end up getting 235 in profit, or not calling food processor, ending up a profit of 240. Apparently 240 is higher than this, so that means over here you will decide to choose not to call the food processor. So I'm going to check this branch to remind myself this is the best decision if Michael ever ends up in this situation. Okay, so also I'm going to put this number over here, okay, just to remind myself if Michael ever ends up over here through ordering 80 and demand is high, then going forward his payoff will be 240 under the best decision going forward. Next, I'm going to move on to this decision. You can see it's quite similar. Let's compare the payoff, 395 versus 390. Apparently 395 is a higher profit, which is preferable, so that means he will choose this branch, and I'm going to copy this number over here. So that again means if Michael ever ordered 140 and the demand is high, then his expected profit going forward from this point on is $3.95 by choosing to call the food processor. Okay, next we can move on to these two notes. So let me label them for convenience. This is note 1, this is note 2. They are circles. So when it comes to circle, you need to calculate the expected value. So here, expected profit. So here, this is an uncertainty, 0.4 chance to come here, 0.6 chance to come here. So the expected value of this note is 0.4 times the immediate payoff of the next note, 240, plus 0.6 times 140. Over here, okay, if you carry out this calculation, it's 180. I'm going to copy this 180 over here. So again, what does this 180 mean? What's its interpretation? It means if we ever get here, in other words, if Michael orders 80, then his expected profit will be $180. Okay? If Michael orders 80 units of the sausage, his expected profit will be $180 under the optimal decision going forward. Okay? His expected profit is 180, assuming that he makes the best decision from this point onward. Okay, so similarly, let's look at this point. So the expected value here is the probability times this payoff plus this probability times the payoff this branch, this number. Okay, you carry out the calculation, it comes out to 12. Okay, so I'm going to copy that number here. Again, that means if Michael orders 140, then his expected profit going forward is going to be 212. Okay, so now we have the payoff of these two notes. We can move on to this one. So should he order 80 or 140? If he order 180, his expected profit will be 180. If he orders this number, expected profit will be 212. Apparently 212 is higher, so that means he should choose to order 140. And I'm going to copy 212 here because that's the expected payoff under the best decision, which is ordering 140. So at this point, we finished the analysis of this tree. Now that we fully analyzed the decision tree, we can answer some additional questions. First, if Michael orders 140 sausages and the weather is good, which means demand is 120, at this point, should he request the food processor? What is the expected profit in this case? So if he ordered 140, that means we start off here going this way. Weather is good, that means then we come here. At this point, what is the expected profit? We already found it. Okay, it's $3.95, and at this point, going forward, he should choose to call the food processor. Okay, so yes, expected profit is $3.95. Next question. So what is the chance that Michael orders 140, demand is 120, and he requests the food processor? First of all, would he ever order 140? Oh yes, it turns out that he should always order 140. Okay? And then demand is 120. Okay, what's the chance of having demand 120? Oh, it's 40%. So that means he has 100% chance under the best decision. He has 100% chance to order 140, and then 40% chance demand is 120, and then he has 100% chance of calling the food processor because that's the best decision. We just found it. So that means the chance of he go here and then here and then here is simply 100% here, 40% here, and then 100% here. So 100% times 40% times 100%, still 40%. Next question. So what is the chance that he orders 140, demand is 120, and he does not request the food processor? That means what is the chance that he will actually go here, and end up here? So first of all, we notice that if he ever ends up in this situation, he should always call the food processor. So that means there's no chance over here he would choose not to call the food processor. So that means his chance of coming here and then here, it's 0 because he would never choose this branch given that he's here. So it's simply 0.